Hello, welcome to the stream processing meetup. It's great to have everyone here. Thanks for coming in on time on this Tuesday evening. I know traffic's never easy this time of the day. My name is Karthik. I work in our streams infrastructure at LinkedIn. My teams work on our PubSub messaging ecosystem built on Kafka, our stream processing infrastructure on Samza, and change capture technologies. We do this meetup roughly around 2 to 3 months apart. So the next one will be in 2 to 3 months. In all likelihood, it will be in our Sunnyvale campus because we recently exchanged our buildings with Google. Getting started, just a couple of housekeeping things. We're going to have 3 talks today. So I'm very excited about the lineup today. Each talk is going to be 35 minutes. So 30 minutes for the actual talk and 5 minutes for Q&A. If you do have questions that go beyond 35 minutes, we're going to stop it at 35 and have you ask questions toward the end. Towards the end, the speakers will still be here, so you'll still get to kind of talk to them and ask your questions. Let's see if there's any other. Yeah, I guess that's that. I think we can dive in. Our first talk is from Jason from Confluent and Onur from our LinkedIn development, Kafka development team. So let's give it up for Jason and Onur.
Are we just both gonna sit up here, like?
Yeah. Okay. See, this is the hardest part. Okay. So, do one of these. Is this on, by the way? Can everyone hear me? Yeah. Okay. So, let's do this. So, okay. All right. Okay, so I'm Onur, and this is Jason. So today we're going to be talking about consumer group internals, and to kind of set the tone for what this is about. Basically, this is not a talk about client implementations. This is specifically a talk about protocols. So basically, the protocol involved with group coordination. And it's also about a submodule within the broker called the coordinator. And I guess I promised the guy on my team that I would do this earlier. So, okay, so this is consumer group internals, rebalancing. Okay, I'm done. So, okay, so next slide, here we go. Right, so before we get into the details here, let's just talk about some of the basics. So Kafka has topics. These topics have partitions. And when you produce into a partition. In order to consume, we have consumer groups. And these consumer groups are Kafka's way of scalably consuming from topics in a fault-tolerant way. And within these consumer groups, we have consumers. And so these consumer groups share a group ID, and the consumers within this group coordinate to distribute partitions of a set of subscribed topics. And hopefully, if we do everything right, these partitions will belong to exactly one consumer of this group. So together, everyone would fully consume all these partitions of the topics that they're subscribed to. Okay, so I loudly stated rebalancing in the first slide 4 times. So what was I talking about there? Abstractly, I'm talking about a protocol for distributing state within a group. And so what triggers a rebalance? A couple things. So one is like group membership changes. So here I'm talking about like a member joins, member leaves gracefully, and a member fails. And also another thing that could trigger it is if member intentionally tries to distribute knowledge of its own state change. Okay, so more specific example of this, I was talking about consumer groups earlier. So in the context of consumer groups, the protocol that we're talking about for the rebalances is a protocol for distributing the partition ownership from the subscribed topics. And what triggers these rebalances are state changes group membership changes of that consumer group, and consumer topic subscription changes. So if a member of the group decides he wants to start consuming a new topic, we could rebalance and consume from that. And if existing topic that we're subscribed to changes its partition count, we need to start consuming that new partition. And so one part of this is, well, how do we decide who owns what partition? So this is decided by the partition assignment strategies. In the old high-level consumer, the Zookeeper consumer connector, we only had two, which were the range and round robin. Now with the shiny new consumer, we have pluggable partition assignment strategies, so you could do your own custom strategy there. Okay. So another desirable property that we have of this rebalancing protocol is to be able to hand off ownership nicely. So if everything goes well, all the consumers that are alive will probably will first checkpoint the offsets that they've last consumed from. We hand off partitions, and when a new partition owns that partition, we'll fetch that offset that we committed and continue processing from there. So we have exactly once processing. We get into the at least once territory when a failure happens with another group. And that could happen if, say, a consumer was consuming some amount of messages and they failed somehow or other before committing offsets. The new consumer picking up that partition will have to start processing from an older committed offset and do some reprocessing. So that's the at least once behavior when failures happen. Okay, so in the past we had the high-level consumer, and this was using coordination through Zookeeper. So by high level, I'm talking about Zookeeper consumer connector, and they get notified of these changes by using Zookeeper's watches mechanism. So here we subscribe to child changes of this group znode path, the consumer's group IDs path, and also data changes of the topics that they're interested in. One interesting property of the Zookeeper-based coordination is that consumers independently run the assignment strategy. That has some interesting properties which we would like to avoid, which I'll talk about later. And so the consumers commit offsets to Zookeeper, and they claim ownership in Zookeeper as well. Okay, let me get some water. Sorry. Right, so let's talk about what we have right now and what we want. So today, with the Zookeeper-based coordination, in terms of access control, you have to define control in two different places, right? We have two systems running. We have Zookeeper and we have Kafka. So we basically, with Kafka 09, we now have security, so we have to define it in Kafka and we have to define it in Zookeeper. In terms of protection, anyone could today just go to Zookeeper and wreak havoc on the cluster. So we would like to avoid that if possible. And in terms of, if let's say you wanted to make your own client implementation, you basically have to have a dependency on Zookeeper, which is something we'd like to avoid. And in terms of decision making, we just talked about how clients independently make this decision without agreement. And it's possible today that any rogue or zombie consumer could commit offsets and basically override a legitimate offset from a consumer who owns a partition. And there's also this kind of a performance or contention issue in the Zookeeper-based coordination derived from the fact that the members claim ownership of certain ephemeral znodes. So okay, that's what we have. So what do we want? Ideally, we would want one place to define access control. So this is a Kafka talk, so we want to define everything just in Kafka. Also, we would want to protect Zookeeper as much as possible, because Zookeeper fails, then Kafka cluster is in a gigantic mess. So we want to protect Zookeeper from client interaction, all client interaction to just go directly to Kafka. We want to prevent dependencies from Zookeeper on new clients. And we actually do want to have some sort of some kind of coordination in the sense that we want a single client to make a decision for the whole group. So that way we avoid a lot of potential issues like, let's say one member of the group is doing round robin while another member of the group is doing range. In the past, they would blindly just try to run those. Now we actually prevent that from happening. So we prevent rebalance conflicts in that way. We also want sort of a rebalance barrier to prevent this kind of a obscure issue of zombie commits from failed consumers. And we want to avoid any sort of contention issues in the rebalance. Okay. Is this me? This is me. So, right, so that brings us to Kafka-based coordination. So this has already kind of been a long time coming now. So in Kafka 082, we introduced offset management in Kafka itself instead of through Zookeeper. So all we're doing here is we're just kind of piggybacking the mechanisms that we have in place from that and augmenting that for group coordination. So kind of the decisions of like where we put, where the group members talk to, which broker it talks to, it's going to use the same protocol as was for Kafka offset commits. Right, so let's move on. Okay, need some more water, sorry. Right, so now we have this thing called Kafka coordination, Kafka-based coordination. So how do we find our coordinator? So this is the basic flow. So a client could query just a random broker in the cluster. That random broker, given a group ID, can determine which partition from the consumer offsets topic that group ID belongs to. And from that partition, we could then associate that with a leader based on that broker's cluster metadata cache. And that leader of that partition is the coordinator for that group. So we tell that to the user, and the client begins coordination with that coordinator. Okay. There's some interesting subtle differences between how we scale coordination in Zookeeper and how we do it in Kafka. So for instance, session distribution. So Zookeeper, a client can connect to any member of the ensemble, and they maintain a session and all requests to that one machine in the ensemble in Zookeeper. Whereas in Kafka, we have all members of the same group must maintain a session to their coordinator. In terms of write batching, our rebalance logic today in Zookeeper basically does individual writes on like a per partition basis, so that causes some performance problems. Whereas in Kafka, we do like one big write. So we batch a write at the end of the rebalance, basically. In terms of distribution, Zookeeper under the hood basically just has like a single transaction log. Whereas in Kafka, we could spread out our writes of the group across all these consumer offsets partitions. So I might have missed that earlier. Basically, we're piggybacking on the Kafka-based offset protocol, which is mapping a group to a consumer offsets partition. And that partition is owned by a broker, and that's the coordinator, basically, for that group. Okay, so in terms of performance, in Zookeeper, performance decreases as you grow your ensemble. So as you get a bigger and bigger Zookeeper cluster, performance degrades because we do like quorum-style writes. Whereas in Kafka, performance degrades as our in-sync replica of that consumer offsets partition increases. So with this, you could actually have a gigantic Kafka cluster and not be worried about write performance because it's only impacted by the replica set of that partition. Okay, This is basically just the same slide as before, but you now see a nice picture. So as you can see, like all the members of a certain group coordinates with just a single broker. Okay. And right, so another thing is that there's many coordinators in the Kafka cluster. That's another thing to bring out. Okay.
Can everyone hear me fine? Okay, so if you look at the group balance protocol, basically what it's providing is a synchronization barrier. So on every synchronization barrier, the coordinator is basically waiting for all of the members in the group to join. So in this example here, we're showing like, 2 members joining the group, and then at every barrier, we create a new generation. So this generation is what we use for basically fencing. So like Onur was talking about, how do we detect zombies? Well, this is basically the way, by a generation. So this number increases every time we rebalance, every time we instantiate that barrier. Yeah, let's continue. So we're going to talk a little bit about the protocol. Kafka itself is a request reply protocol, and the different requests that are involved in this rebalance process are these ones. Really, the first 4, the last one is kind of an administrative API, but basically, we've got a heartbeat mechanism which we use to detect when consumers fail, and this join and sync, which we're going to talk a lot about, are the actual rebalance itself. And then leaving is kind of our way for a member to cleanly leave the group. So after we rebalance and we have a new generation, what the clients do is they start sending heartbeats to the coordinator, and basically periodic heartbeats. And the coordinator has like a session timeout, after which if it doesn't get any heartbeats, then it's going to declare the member dead and it's going to start a rebalance. And the mechanism for when we detect that, when a rebalance has begun is the same thing. It's this heartbeats. So when a rebalance begins, a new member is going to come along, send a heartbeat, and we're going to set an error code in the response saying rebalance is in progress, so you need to rejoin. Let's keep going. On the coordinator side, what this looks like, it's kind of a typical heartbeat mechanism, kind of what you imagine it would look like. When we receive a heartbeat, we set a timeout basically for when that time that we received it plus session timeout. When we receive the next one, we just keep on incrementing it. And if the timeout ever expires, then the consumer's dead and we rebalance. So let's talk about the rebalance process itself. So after we've detected a need to rebalance, there are 2 phases to this process. So the first phase is kind of like the first phase is actually the barrier. So it's when all the members in the group join, they send a join group request to the coordinator, and after all of the members that we expected to join, like all the ones that were in the previous generation, then we return from join group, and then we do this extra phase, which is kind of like this state synchronization phase. So let's walk through how this works. So now we're presuming that we have kind of a stable group already, and we have 2 members which are sending a join request to a coordinator. Join request itself, it includes some kind of an ID which we use in order to identify the member, and then we include the list of topics, like the subscribed topics that we're interested in. Because the main thing about the rebalance that we're trying to do is distribute the partitions, so they have to tell us what topics they are interested in. In this case, we're showing subscriptions that differ, but typically they're the same. After all members have joined, all of the the synchronization barrier has completed, then the coordinator will respond. So until we get all of their join requests from everyone, we just hold on to that request. So internally we have a purgatory implementation, which until the rebalance completes, we just keep it in purgatory. As soon as it completes, we send back this response. So this part is kind of interesting. So in this response, the coordinator is going to elect one of the members to be a leader. The leader's job is basically to do the partition assignment. So we'll get into the reasons for this later, but from a high level, what it does is the coordinator is going to send all of the subscriptions to that leader. And for everyone else, it's just going to send a kind of an empty message saying, your leader is A, and here's your new generation. So after we have this, the leader itself is going to begin doing, running its partition assignment algorithm like round robin or range or whatever. And once it's complete, then we're going to proceed to this next phase, this sync phase, like a synchronization state synchronization. So that leader is going to determine who should get which partitions, and it's going to send it back to the coordinator. And then the coordinator is basically going to collect it. So, I mean, there could be like an ordering issue here, like member B sends a sync request here first before the leader has sent its assignments. And we do the same trick that we do everywhere else, which is we just hold it in purgatory until we're ready to return. So and then when we return, we collect the assignments from the coordinator, and then we're ready to start processing. So this is just a way to kind of communicate the partition assignment through the coordinator. We talked a little bit about like this two-step phase, and why do we do this? So the main reason is, I think in the initial implementation of this, actually, the assignment was done on the server side, but we found it to be a little bit restrictive in terms of the kind of capabilities that we might want to have. So there are a bunch of different more complex assignments. Like range and round robin are quite simple, but there are more complex things that you might want to do, such as like sticky assignments. So sticky assignment means like we take into account what the previous assignment was. Rack-aware assignment. So recently, I think in 09, we added support, maybe 010, I forgot. We added support for rack awareness in Kafka, and it might make sense to have consumers, take that into account when assigning partitions. Resource-based assignments, like, if there's some kind of like difference between, maybe one consumer has 4 CPUs, another one has 8, you might want to take that into account when assigning partitions. So putting it on the client side basically lets us gives the control to users, so you don't need like a code push to the server in order to get kind of a new assignment strategy.
Okay, this is me. Okay, so we kind of talked roughly about the join and the syncing phase, but there's some state on the coordinator itself. So at the very least, we need to have this state machine for each group. So basically, I'll talk about each of the states and what they involve. So basically, there's a stable state. This is just a normal state where members heartbeat and they're allowed to commit offsets. There's the preparing rebalance state, which is basically when the group is rebalancing and waiting for join groups. And we notify members that a rebalance is happening through the heartbeat response. There's the awaiting sync phase, which is where we're waiting for the leader of the group picked by the coordinator to provide its decision based on the member state. And there's these 2 other states. I'm not going to go into too much detail. They're more or less for cleanup reasons. I'm not going to go into detail on those. Okay, so I'm going to go into 3 examples, maybe 4 if we have time. One is simple member join. Another one is member failure, and the other one is the member leave. So we'll kind of walk through what actually happens. One sec. Right, so, okay, so here we have consumer 1, and he's heartbeating to its coordinator. So something that he says is, okay, I'm member 1, I'm in group G, and I believe that my generation is 1. And the coordinator basically says, okay. And we do this regularly, so this is happening all the time. Okay, so now something interesting happens. A new consumer tries to join the group. So here, he says, I'm new to the group. That's why I have like a question mark down there, because we don't know our member ID yet. You should consider me dead, basically, if I don't heartbeat within S2 time. That's the session timeout. And here's my state. Here's my subscribed topics. Okay, so next time consumer 1 heartbeats, if it's after that state transition, after the preparing rebalance state transition, then we notify in the heartbeat, okay, it's time for you to rebalance. Something has happened, basically. So he sends a join group now saying, okay, I'm M1, I'm already in this group. You should consider me gone if I don't reply within S1 time. And here's my subscribed topics. Eventually the joining phase finishes and the coordinator picks a leader. In this case, he picks consumer 2 as the leader of the group. And he gives the leader some interesting information. He gives the leader all the members and all of their state. That's enough information for the leader to make some sort of a decision. And now we kind of begin the syncing phase where consumer one sends a sync request waiting for the leader's decision. And consumer two, the leader, has made a decision. He provides M1's assignment and M2's assignment. And now the group is stable. We have the decision, right? So the coordinator then basically broadcasts to each of the consumers each segment of the leader's decision. So here's M1's assignments, here's M2 assignments. After this point, they just heartbeat, have a great time. And one interesting thing is that the generation ID has incremented after the join group response right here. So generation ID increments here. That's important. Okay, so that was join. Now we could go over member failures. So now we're continuing off the previous example where consumer one and consumer two are heartbeating. They know that they're in generation two. And after some time, consumer one fails, right? So, sorry. So after some time, consumer one fails. And the coordinator realizes that his timeout expired, basically. His session expired. So we transition to the preparing rebalance phase. The next heartbeat consumer two has, we notify him that it's time to rejoin. And this is very similar to what we saw before. So consumer two gives the coordinator his state. He tells him that he's member two and the topics that he's subscribed to. Coordinator replies saying, okay, you're the leader. Here's everyone's state. In this case, it's just member two state. Consumer two makes a decision based on that state. We're stable now. The coordinator replies with everyone's assignments, and we heartbeat. Okay. So we would ideally like to, if we know that a consumer is going to leave, we would like to rebalance quicker, right? We don't want to wait for that full session timeout if we can. So that's why we have this leave group request. It's going to be very, very similar to what we saw before. So now imagine that we're in generation two and everyone's heartbeating, but we know that consumer one is going to leave. He tells the coordinator, I'm going to leave. And the coordinator's like, cool, thanks for letting me know. Basically, we've transitioned to the rebalancing, the preparing rebalance state. And we tell consumer two in its next heartbeat that it's time for him to rejoin. He rejoins with his state. Coordinator picks him as the leader. We make a decision. We tell the coordinator our decision. Coordinator replies with everyone's decision. And we start heartbeating. Okay. This one's not, we don't need to go into too much detail on the committing offsets. All I'm going to say is basically, we could heartbeat as long as we're in the same generation. This is the fencing property we talked about before to prevent the zombie commits. So when we commit our offsets, we provide a generation ID, and the coordinator will validate that generation ID. So here, the group is stable, and we're doing an offset commit. And even during rebalance, we're allowed to still offset commit because the generation ID bumps at the end of the rebalance phase. That's pretty much all we had to go through in that one. So, yeah.
How much time are we at? Okay. So let's try to go quickly. So rebalance latency, I think this is something that usually people care a lot about, so it's important to kind of break it down a little bit. So these are different components, and we'll talk about kind of like what you can actually affect. So the first thing is the heartbeat interval. So in order to detect that a rebalance has occurred, we use these periodic heartbeats. So if we, in the best case, we're able to detect it right after, but kind of in the worst case, it takes us a full heartbeat interval in order to detect that a rebalance is needed and we need to rejoin. So after that, if you go all the way back to the beginning of this talk, we talked about the consumer semantics. And basically, as soon as we detect that a rebalance is needed, the first thing we need to do is complete whatever current work we have going on and commit offsets. And that's going to be, all of that time is what's going to hold back your rebalance. And the offset commit itself, of course, that has some latency. And then once we join the group, we've got to wait for everybody else in the group to do the same thing. And yeah, usually like the assignment itself should go pretty quickly. So the main things I think to take away from this are, you can't really impact the time to commit offsets, and really you don't need to because it's fast. And the assignment as well is fast. So the main things here, if you want to have, like a faster rebalance, the main things are the heartbeat interval, so you can heartbeat faster in order to detect it quicker. Or you can reduce the time to consume basically the last return records. And the way you do that is basically by handling smaller chunks of data. So we don't have the API up here, but for example, like the consumer has a max pull records setting, which lets you get smaller chunks of data and lets you rejoin the group faster. Okay, let's go fast. So the coordinator itself, it's maintaining all of the state about the group inside the log. So we had that consumer offsets topic, which we're using in order to determine who the coordinator is, and then that's where we're storing all of the state. So as we're committing offsets, we write it to the log. As we rebalance, we write it to the log. And in memory, we keep a materialization of that log with basically everything up to date. And the important thing here, yeah, we write with ax equals all so that we have up-to-date replicas.
You can skip that.
Yeah, let's skip this. So let's just go through the coordinator failure. So this shows why the log is important. So normally, we're sending heartbeats to the coordinator. When the coordinator crashes, the consumer will detect it like a socket disconnect or something, and it's going to go into kind of a find coordinator phase where it goes and asks any one of the other brokers, who's my new coordinator. It can take a little bit of time for the cluster to converge, depending on the type of failure. Maybe it depends on like a Zookeeper session timeout, for example. So we have to spend a little bit of time where we retry. Eventually the coordinator, the partition is moved over, and the coordinator is moved as well. And then we're able to continue heartbeating. And the trick behind this is that when the partition migrates to the new leader, we reread that entire log from the beginning in order to build up the state. So that includes the state of the generation, all of the offsets. And then so from the consumer's point of view, they just start sending heartbeats with their old generation, and no rebalance is needed. Let's skip that.
I can cover that.
Okay.
Yeah, so quickly, some future work to be done. So as Jason said, all the group state is in memory. So there probably will be, there might be an issue of memory pressure when we get to more heavy use cases. So maybe what we could do is we could just keep an index and point it to the location in the file, and then we can just read from the file. So today what happens with heartbeats, we basically have very fast responses from the coordinator. So we send a request and we respond to the heartbeat immediately. This could lead to a scenario where we basically might just barely miss the notification for a rebalance. So one thing we could do is instead we could have the coordinator hold on to the request for some amount of time to increase the odds of us catching a rebalance. So there's some like nice pictures here that basically show you what that might look like. Anyways, right. And the other potential future work is maybe we could push in regex subscriptions into the protocol. So today we have clients fully expand their regexes when they, let's say they do .star. They provide the full list of topics in their rebalance, in their join group. This can be a problem because consumers independently pick up metadata of the cluster. So you might have a worst case scenario where one member discovers a topic, rebalances the group. Another member discovers a topic, rebalances the group, and so on. So instead, what we could do is just push the regex into the protocol. So the group leader could be the only one deciding that we need to do a rebalance. So we drastically would reduce the amount of rebalances. One thing we might need to do there is like agree on a regex protocol. Anyways. All right, and then there's also potentially, this is a little bit more drastic, but we could maybe only rebalance some members of a group. So maybe we have a rebalance, a partition assignment strategy where we only impact a subset of the members of the group. It's kind of wasteful to make everyone stop, rebalance, and start up again. What we could do instead is maybe add like another third step to the rebalance protocol to make the leader like figure out who needs to actually go through rebalance. I don't know. Okay, yeah.
So adoption. So of course we've implemented this in the Kafka clients. We have some other languages as well, librd Kafka, C++ client, Kafka Python, they've implemented this. These other two ones, the Confluent ones, these are based on librd Kafka, but I'm counting them anyway. And I don't know a lot about this Erlang one, but apparently they support it too. So we're already seeing, so this was one of the big reasons why we moved to the Kafka coordination in the first place, is to make it easier for clients in order to develop the consumer group protocol. So and it's also used, of course, in Kafka Connect and Kafka Streams.
Cool. We had more like a lot of appendix stuff, but. Okay. Okay, 2 questions. Yeah. So, yeah.
I have a question regarding to the comment on the sticky assignment thing.
Okay.
So,
Yes, do you want
the
to do
question is, okay, where do you store the particular assignments from the previous one?
Yeah.
The whole groups of the consumer test.
Yeah. So let's go that. So inside, if you look at the protocol that we're using, so basically like subscriptions are communicated inside. So this is like inside our join group, and we have this this user data field. So this user data field can be, and actually this is what Kafka Streams does currently. So we use it uses this user data field in order to communicate the last partitions that were assigned to that member.
Okay, so that part of the metadata is pretty much stored on Zookeeper.
It's stored in, it's stored in the log, like in the consumer offsets log. Yeah.
Okay. Do we have time for one more? Okay. Yeah.
You mentioned that each client can decide what its timeout value is going to be.
Right.
Can you elaborate on why this decision was taken versus, let's say, having the leader of the group decide what the timeout is for everyone or something like that?
Yeah, so that's an interesting question. So let's see.
Are there any use cases that benefit from variable timeout, or are there only?
Yeah, I think usually they will be the same. Maybe like during an upgrade, for instance, there might be different values there. But yeah, usually it will be the same.
Yeah, I think, to be honest, I never actually thought about it. I think even on the coordinator, I think we maybe even just take the maximum. I think really maybe we didn't have a use case for pushing it to the leader is really the answer. So letting them decide their own session timeout. Usually we're talking about a consumer group which is using the same configuration. So the only time you'd really see them diverge is in the case of a rolling upgrade or something like this. And in that case, it doesn't seem like it's actually a problem if they're different.
But the time that it takes before rebalance can begin is the maximum of
Yeah.
In fact, it's So this is one thing that's a little bit different in. Sorry, I guess we're going way overboard. But so there's this KIP62 which introduces a rebalance timeout, and we can talk about it offline.
Thank you so much.
Thanks.